Hey everybody, Miss Aninga back to help you with covalent bonding. I first wanted to step back and give you the answers for the one above up here, just so that you can check your answers. So you remember we did the first three over here before. I went ahead and did the rest of them. I put in both my formula, and I also have my charges that show you how I came up with my numbers for each of them, for my little numbers down here, or here, or here, just to give you an idea of the thought process on how you find your complete formula for ionic bonding. So feel free to pause and double check your answers with that. Otherwise, I'm going to continue on to covalent bonding here today. So, again, up here, something good to read to help you out. Otherwise, covalent bonding is all about, like ionic bonding was about transferring or giving up electrons or taking them up. Covalent bonding is not about that. Covalent bonding is about sharing. The sharing is caring bonding. I'm going to switch to red, if that's okay. So covalent bonding is all about sharing, and because this takes place between our nonmetals, which are the players that are over here on our periodic table. In covalent bonding, we do not deal with these guys over here at all. No metals at all. We all deal with the nonmetals, which are over here. Okay? And as you can see, all of these guys want to gain electrons. So that means when they're bonding, they're stubborn and don't want to give electrons up, but they're okay if they share them. So covalent bonding happens between our nonmetals, all about sharing. So over here we have some examples where we have two fluorine. It says each has 7 electrons, valence electrons. So you can count them, 2, 4, 6, 7. Same over here, 2, 4, 6, 7. And they each want to have access to 8 electrons. Okay. What's interesting about covalent bonding is each of these fluorines say, I have an extra one. And they look at each other and say, you want to share these? And the other says, yeah, I do. And so they share this electron with each other. So this fluorine will share this single electron with this one, and vice versa. This one will share this electron with this fluorine. That way they both have access to 8. 1, 2, 3, 4, 5, 6, 7, 8. And for that one, and 1, 2, 3, 4, 5, 6, 7, 8 for that one. And so they share it, which makes a bond between the two. Okay. Sometimes you share more than once with either the same element or with different elements. So for example, over here with oxygen, oxygen has 6 valence electrons in each, and they want to have access to 8 of them. So what they do is they go, well, if we share 1, now we each have like access to 7 electrons apiece. But what if we share 2 of them? If they share 2 pairs of electrons, so this one shares both of these with this oxygen, and this oxygen shares both of these with that oxygen, now you see they both have access to 8. 1, 2, 3, 4, 5, 6, 7, 8. Or 1, 2, 3, 4, 5, 6, 7, 8. So it's all about sharing pairs of electrons. the more bonds, the more pairs that you share between, so the more electrons you share, the stronger the bond between the two elements. It's almost like each of these is an arm. And so, like, if you played Red Rover, this, like, if, you know, people were holding just the one hand together, it's easier to break than if people were holding each other, like two pairs, if they were holding both their hands together. So, yeah, more arms / more bonds, harder it is to break. Okay? That's the basics behind covalent bonding. So, I'm going to keep going here. I know we're already, you know, getting into a lengthy video, but just, you know, bear with me. Coming to the critical thinking questions. Some of the wording in here can be kind of confusing, so I'm going to try and help you out with that. When the nonmetals are not in the same group, one atom shares electrons with several other atoms. Consider the formula of a compound containing sulfur and chlorine. Down here, this is telling you how it can share. So chlorine and sulfur share here and here. To achieve 8 electrons on each, they have to share. So that's how that one works. Down here, this wording might be crazy. So it says, how many electrons do the elements below need to form an isoelectric configuration with a noble gas? Okay, that's a big sentence. All that is saying is how much does this element need to gain in electrons to be equal to that of a noble gas. So, for example, we look at hydrogen. Hydrogen, which is, well, ion, it's lonesome over here. How many electrons does it need to have a full valence shell, which is over here? It needs 1, correct? Because down here you need 2 to fill up the valence shell. So in order to get the same configuration as of electrons as a noble gas, hydrogen only needs 1. Okay, next one, carbon. If you look at where carbon is, carbon's here. It has 4 valence electrons. How many electrons does it need in order to become like neon at 8? And that answer, of course, is 1, 2, 3, 4. Okay? So it needs 4 electrons. Nitrogen needs 1, 2, 3. So on and so forth down the line. Okay? And then finishing up with 3. 3 says, each covalent bond leads to each atom involving gaining 1 electron to its total. How many bonds does the elements below need to form an isoelectric configuration with a noble gas? Again, this is asking how many bonds it needs to make in order to get to that 8 that it would have as a noble gas. So hydrogen, it needs 1 electron, which means it needs to share once to gain an extra. So it needs 1 bond. Carbon needs 4 electrons. So in order to get that, it needs to share 4 times. Nitrogen needs to gain 3, so in order to get 3, it should share 3 times. So on and so forth. So far you should notice a pattern between 2 and 3 all the way down. Alright? Alright. coming to the back here, we will see that we were looking at different stuff here. Up here, it wants you to look at each of these different molecules, and what it wants to know is when you count the valence electrons that are around each of your atoms, what do they equal up to in each of them? So, for example, for up here, I accidentally started before getting to our video, but in any case, we'll look at the fluorine one first. So fluorine, each of our fluorines will have, and if we look at each of our atoms and count them up, including the shared electrons, we'll see that we have access to 1, 2, 3, 4, 5, 6, 7, 8. And this fluorine has 1, 2, 3, 4, 5, 6, 7, 8. So each of our valence electrons for fluorine is 8. Okay. Do the same for oxygen, chlorine, and sulfur. Down here for number 5, it wants us to draw out our chemical formulas that it gives us here by showing it kind of similarly to these ones up here with our Lewis dot structures with our little dashes to show bonds. Okay, so I'm going to break these up and I'm going to do them on paper for you so that we can see it in a bigger picture. So the first one that I'm going to be doing is NH3. Let me silence my phone so it's not ringing all the time with mail notifications. So we got NH3, which is our first one right here. I'm going to use a few different colors. I will use my blue again. I'm going to use red and black if need be here. So if we look at our equation here, our formula, excuse me, we can see that it is broken up into two pieces, into two elements, one being nitrogen and the other one is hydrogen. Now I'm going to use those colors for each of those. But you'll notice for nitrogen, we don't have a number next to it down here, which means that we don't have more than one nitrogen, whereas hydrogen, we have this 3 down here, which means that there are 3 hydrogen. Okay, so what I'm going to do is I'm going to lay these out, giving space in between each of them so that we can clearly see what's going on. I'm going to put an N there. I'll put an H over here, H up here, and an H over here. Now, once you have things like spread out, you want to add your valence electrons to each of these. Nitrogen, according to our periodic table, has 5 valence electrons. So 1, 2, 3, 4, 5. Whereas hydrogen has 1. Oops, wrong color. So each hydrogen has 1. Okay. So now that we have our valence electrons, we need to start showing our bonds, so our covalent bonds that we have. So we'll notice that in our Lewis dot structure of nitrogen, it has a full, like, 2 set over here, but we have 3 lone ones on each side. Nitrogen needs 3 valence electrons to get to 8. Hydrogen needs 1. So it's kind of convenient that this lonely one here can match up with this lonely one here. So that's what we'll do. We'll bond. If we make a bond here for each lone nitrogen valence electron with the hydrogen, notice hydrogen has access to 1, 2 electrons. That makes it happy. That's every single hydrogen. And nitrogen now has access to 1, 2, 3, 4, 5, 6, 7, 8 electrons, which is what it wants. So this is the correct drawing for NH3. Okay? So we did this one. Many of the other ones are very similar. You just have to lay stuff out evenly and then draw your valence electrons and then connect them. Some of these equations are confusing to look at and maybe are head scratchers. So for example, like this first one right here, CH3NH2. Okay. This one is a little bit different because you'll notice you have hydrogen in 2 spots. And so it might be confusing to look at. What this is telling you is that there is actually 2 molecules kind of bound together, which is CH3 and then NH2. What you should do with molecules like this is you should try and break them up as they are written to see if you can't then connect those 2 together later. Okay? So for this half, I'm going to use red for the carbon and then blue for the hydrogen. And then over here I'm going to use blue for nitrogen and red for hydrogen. Okay. So I'm going to make my first side, which is CH3 over here. So C over here. And then I'm going to put H's around it. If we take a look, carbon has 4 valence electrons. So 1, 2, 3, 4. And hydrogen, like we talked about, has 1 apiece. Carbon, thankfully, is very diverse, and it has 4 electrons, allowing it to bond, with on any side, which is great. So, same as before, our hydrogens is going to share over here. Now, the reason I'm not connecting them together is because C here on the end implies that it is the main connecting point for our other ones here. Okay? So this is what this half will look like. Notice I have a spare valence electron. This is good. I'm going to move on to this one here. So I have N. And then I got 2 H's. I'm going to put them on either side, up and down. Nitrogen has 5 valence electrons, like we talked about. So 1, 2, 3, 4, 5. And each hydrogen has 1. Hydrogen can, of course, share with a lone pair. And notice the only lone pair that I have, lone electron I have left is 1 on each side. So notice I didn't link any hydrogens together because obviously these hydrogens already are connected to the main piece. That's the same thing here. This N here kind of implies that it's the main piece that hydrogen is attached to, or at least these hydrogen. That's why they're split up. So in order to connect them all together, we'll just connect the lone electrons together. So this implies, so with our structure, that they're all connected together as one entity instead of two separates. So all together, it may look like two separates on paper here in the formula, but that is good because that helps us to determine the structure. Okay, but this is what the structure will be for CH3NH2. Okay, let's see. The rest of these, just like for these ones, make sure you're just laying them out and cutting them up, like separating them based on what we did before to make a coherent like structure drawing. Okay, back here I'm going to tell you that numbers 6 through 8, so this whole section here, is optional. Okay, you do not need to do numbers 6 through 8 because they talk about something a little bit more complicated, which was the exception to our octet rule, which of course is the 8 electrons around in the valence shell to make a covalent bond. Instead, it breaks that rule with our exceptions, and you'll see things like sulfur here in the middle having 2, 4, 6, 8, 10 valence electrons. And so this is a little bit more complicated. This is more like a actual chemistry like section here, so I'm not gonna have you worry about that. So you can try it if you want to, but I wouldn't worry about it. And then finally, coming down to model 3, the last bit of your assignment here, of your packet, just wanted to make a couple things clear. First thing is, this is looking combining the ionic and covalent idea. So you're excuse me. So you're looking at if something is a covalent or ionic bond in this section. So number 1 says predict whether the bonding in the oxides following elements will be covalent or ionic. So the word oxides simply means that what's gonna happen, predict the bonding type if you took this element and bound it with oxygen. Okay, so if you take sodium, which is over here, and oxygen, and you bound them together, would that be a ionic bond or a covalent bond? Hopefully, based on what you remember reading, ionic bonds form between metals and non-metals, whereas covalent bonding happens between 2 or more non-metals. So based on that, sodium and oxygen, one is a metal and one's a non-metal, which means that this will be an ionic bond. Okay, whereas like silicone and oxygen silicone and oxygen. They're both non-metals, or one's a metalloid and one's a non-metal. That still means they're both non-metals. This means that this will be a covalent bond. Okay? And then when we come down to number 2, it says write down the formula of each oxide. This just means that you're just going to have to go through and write your formula for this. So just follow your rules for ionic and covalent bonding. I'll do these two for you. So for A, we have sodium and oxygen. Sodium, remember, is a +1. Oxygen is a -2. +1, -2. So in order to make this balanced, -2, we have more negative than positive, so we got to add more positive against the negative, so we should have 2 sodium. Okay. For D, since this one's a covalent bond, I'm going to do it quickly on here just to help you out. We have silicone and oxygen. So if we label them out, it's, silicone has 4 valence electrons. Oxygen has 6. So draw them out. I'm going to do it like that, and you'll see why here soon. Oxygen needs 2 to be happy. Silicone wants to share 4. Silicone can share twice, but oxygen after that doesn't want to share anymore. So what silicone does, yeah, sorry, silicone is Si, my bad. So what silicone has to do is it kind of has to look around and say, hey, do you have a friend? Do you have a brother that could give me, like, share to? And oxygen goes, yeah, I do. So that's what ends up happening, since the only players that you can involve are silicone and oxygen. We don't need any more silicones. We needed another oxygen. So in order for silicone to be happy, we needed to involve 2 oxygen atoms. So your overall formula then is SiO2. So you'll notice with this one, we didn't have any charges or anything because it was covalent. So this one, you might have to end up making a drawing, like so, to get through the covalent bond ones. The ionic ones, you just need to know your charges and being able to balance those charges out. Okay? So that should do it for the packet. Just try and do those over and, you know, see how you do. I'll be posting this as an answer key here soon, so keep an eye out for that, but do your best on this and let me know if you have any questions. Otherwise, that is the covalent side of your packet, and hopefully that helps you out. Otherwise, I'll talk to you all later. Bye.